Okay. All right, so we're going to do just a little bit of a programming session, and we're kind of going to go through setting up transformation matrices in the code, setting up some combined transformations and looking at how that, yes?
If you're recording, shouldn't you be having...
It records my voice good enough.
Okay.
Just from here, I hope. Otherwise, we'll just record it again. Okay, so anyone who's watching the video can pause the screen here just to see how the circle thing looks in my implementation. So this is just what we were doing in the last lab class. So a question, like I've already made a little bit of this matrix class here. I'm wondering, would you like for me to just like walk through that, or should we rather actually go through building the whole thing again? I think we have time if you want to like do the entire thing over, like this kind of stuff. Should we copy that and paste it back in, or do you want to go through the entire thing? It's your choice.
What the fuck is that?
It's a matrix multiplication. It's really simple when you do it on a piece of paper, but as soon as you put it up in code, it's just this huge chunk of code. Should I go through making that again for everyone's benefit, or just leave it up there and trust it? All right, let's just go through this matrix class, because I'm going to make another one. This is kind of just my base. So what I did was simply I went to the package that I'm using here, did new class, called it matrix, and then nothing else. I gave it this here single variable, or class variable, which is a float buffer, and I initialized that here to a float buffer with 16 values. I'm using the float buffer simply because libgdx expects the matrices that we send into the shaders to be formatted in that way. Otherwise, I usually kind of like just working with regular float arrays. But the float buffer, you can initialize it from an array. So if you like working with the arrays and then initializing the float buffer, feel free to do it however you want. The only thing I don't like always about Java is that if you leave a lot of stuff hanging around, you'll sometimes get these kind of pauses in your program while it's garbage collecting. So I try to make as many of the things that I do kind of make a variable for it and change values, rather than always making entire new buffers all over again. But sometimes you can't help that. So this code here, load identity matrix, the code was already inside this base class here, the base game class that I have online in the base project. It already has this code here, clear model matrix, and I just use that same thing. And what it simply does is that it puts an identity matrix into the matrix. So just to put a little bit of a kind of comment explanation here, the way the indexes in these buffers for the matrices are set up are like this: 0, 4, 8, 12. I just need to allow me to keep it one step back here. All right, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12, 13, 14, 15. Okay, so this is the way. Can you see that properly on the screen here? Let's see if it's better visible like that. So the main thing is that it's simply an array or a buffer of 16 values. So it's not a two-dimensional array, but it's representing a two-dimensional matrix, a 4x4 matrix. So just remember that the first 4 numbers are the first column rather than the first row. And also, in these, when we're looking at the transformation matrices as representing a coordinate frame, like an alternate coordinate frame that we're going to be drawing into, the first column is basically the first vector, or the x-axis. And when we load an identity matrix, we're simply setting M0 to 1. We're setting M5, which is this one, to 1, M10 to 1, and 15 to 1. So you can see that down here. The rest of them are set to 0. So we're loading an identity matrix, which we can also see will be 1, 0, 0, 0, which is a vector which is 1 in the direction of the x-axis and 0 in the other direction. So it's basically the base vector for the base coordinate system. The second one will be 0, 1, 0, and then 0, making it a vector. The last one, 0, 0, 1, which is simply the z-axis, just a unit vector parallel to the z-axis. And the last number, 0, 0, 0, make them vectors. The last one has the coordinates 0, 0, 0, but for the homogeneous coordinates, we have a 1 in the end, making it a point. So it's the point 0, 0, 0, which is the point of origin in the base coordinate system. So the identity matrix is basically that, the base coordinate system with the point of origin as the fourth column and the x, y, and z axis, so to speak, axis vectors as the first, second, and third column. Okay, so that's simply what we're putting in here. I added this function here as well, and this huge blob is simply taking two matrices and multiplying them together. And what I call it is add transformation, because I take the original matrix that we're using, that this matrix class is keeping, and I take the second matrix, which you call M2 here, and I multiply those together. I multiply M2 on the right side. So I make these M0 to M15 variables, taking the matrix multiplied values, and then I end up putting them in the matrix. If we were to put it straight into the matrix, I'd be ruining the data that I have to actually use to make the variables to begin with. So we can see, well, it's hard to actually read it from here, but the first column, let's do this one here. Well, good enough. So, okay, so multiplying two matrices together here, and so the first value, if we have, well, the first value is basically this value times this value plus this value times this value, making it the index 0 of the first matrix times the index 0. Then we have the index 4 in the first matrix times the index 1 in the second matrix, the index 8 in the first matrix times the index 2, and then the index 12 times the index, and then we go so on and so forth. So the second one will be this one, making it index 1 times index 4, index 5 times index 5, index 9 times index 5, 6, and so on and so forth. So that's what we're doing there, and it simply looks like this. The first line here you can see is just first matrix 0 times the second matrix 0 plus the first matrix 4 times 1, 8 times 2. So we're simply meshing these two matrices together, and that's just this base operation that we have here. Finally, I took code again from here, and we can look at that part a little bit in more detail. Here, where we're making the model matrix. So eventually we can take this code away, since we're going to be doing that through the matrix class. But for now, what we're doing, we're loading this identity matrix. You can see the indices here as well, 0, 1, 2, 3 for the first column. So I'm loading an identity matrix here. We're putting it in a float buffer, and then we call this. And this is simply us telling OpenGL that for a location in its shader, which we've loaded into this variable, So we did that before here, where we have the model matrix location, and we're telling OpenGL we have this rendering program, which is its shader program. Inside that program we have this variable called the U_model matrix. We can look at shaders in more detail later on. And we're saying we want to get this uniform location here. We want to get some kind of pointer to the location of that variable. So whenever we want to change that variable in the shader, we have some kind of index or some kind of pointer to that. And we do this with a lot of things in the shader. But in the end, whenever we want to actually change the model matrix that we're using in the shader, and we want to do this for every different thing that is drawn in a different place, we have to say everything that is sent through the shader from now on has to use this matrix. What we do is we call this function here, saying we have the location for this variable in the shader, and this is the matrix that we're going to send in there. And what I've done inside the matrix class is simply we say we're not going to store this inside the matrix class. This matrix class is general, so it can be either a projection matrix or a model matrix or a view matrix, depending on what we're using it for. But we say if you send me a pointer, I will take my inner matrix, which is this matrix here, this main class here, and I will load it into OpenGL's current shader program using this pointer. So that'll be the whatever shader matrix pointer is sent to me. In our case, we're going to be using the model matrix shader. Does this make sense so far? It's not. It doesn't have to be super complicated. The idea is just we need a way to send this data that we're going to be manipulating into OpenGL. So when we make this matrix class here, we're going to make another matrix class called model matrix. We're going to add some specific transformations into that and find ways to actually add those transformations on top of one another. But however many transformations we do inside some matrix class that we make, we're not talking to OpenGL. We're not talking to OpenGL until we say, well, we're content with the matrix we've made now. We are now going to set it as the actual shader matrix inside the model view matrix. So that's what we use this for. And that's basically my base matrix program here. We can load an identity matrix, basically making the matrix do nothing. We can add two matrices, that is, take a different matrix and have it multiplied with the matrix that we're working with, and then we can send it to OpenGL into whatever matrix location we want. So now I'm going to make another class. I'm going to call this class model matrix, and matrix. So we'll use our matrix. So we have some classes here as well in some of the kind of base Java libraries that you can use if you want to use shortcuts for that. That's cool. But for now, we're going to kind of make it from scratch just to get to the core of it. So we're going to make this class model matrix, and we're going to have it inherit from matrix. Let's see how that looks. Okay, I guess the first thing we need to do is matrix how was the calling of the base constructor in Java again? Or am I mixing it up with C++ here? Let's see if it complains when we... Or can you do public model matrix. Let's say, so can you just call super? Yeah, that's the way. Okay, so what model matrix does now is it simply just initializes a matrix. Okay, so our idea now is that we want to build specific functions here that add specific transformations. So if we make public void add translation and say we have some values here, translation x, translation y, and translation z. So in this exercise I'm only going to be displaying stuff in 2D.
The parameters right there.
How so?
Like if it's an integer or float. Like
doesn't complete. Yeah, true. Stressed out with the recording or something. All right. Okay. Fair enough. So we want to add a translation, and we could actually now just make a translation matrix, and I hope this OneNote stuff will show in the end. So what we could do is we could say, oh, why am I doing it like that? Like so. Okay. So we could say we just have the current matrix, whatever that is, with some values in it. I'm not even going to put specific numbers to them yet. It's always going to be like this because we're doing affine transformations. And then we can just build another matrix that'll look like this, which is our translation matrix. So, and then we have tx here, ty, and tz. So we could build this matrix here, and then we could call the add transformation and do the whole matrix multiplication. But we can now actually do a shortcut, because if we look at this particular transformation and say what are we going to end up with, we can see that when we multiply this with this plus this times 0 plus this times 0 and so on here, so we end up this times 0, this times 0, this times 0. So we're just going to end up with the same value there. Go to the next one. This times this 1, this times 0, this times 0, this times 0. If we go through this, we'll see that this entire part is simply going to be unchanged. So this part is going to be unchanged, the first 3 by 3 matrix. It's still going to be an affine transformation, so we're going to end up with the bottom line unchanged. So we only really need to put new values into 3 places in the matrix, and those are these 3 places. You can look at it as well. If we were doing it the other way around and adding the transformation from the left, so the transformation matrix would be the left matrix in this multiplication. What would actually happen is that we would simply add these numbers to these numbers. And that's what would be done in classic linear algebra. Classic linear algebra says all transformations are just done from the base coordinate system. And so this transformation would simply be added to that. We can look at how it looks in a picture later on. However, when we're transforming the coordinate frame, we're transforming the coordinate frame within itself. So we don't want to count tx, ty, and tz within the base coordinate system. We want to count it using the vectors of the coordinate system, or the coordinate frame that we already have, which is this. And we can see when we multiply it to the right, what we're going to end up with here is this value here times tx. So we have m0 times tx plus this value here, which is m4, plus m4 times ty, plus this value here, which is m8 times tz, and plus, sorry about that, I'm off. Do it like that. No. Eraser. So, okay. So, times tz plus this value here times 1, which is, so that's m12. And then the rest of them will be the same. We'll have m1 times tx, we'll have m5 times ty, we'll have m9 times tz, and then m13 times 1, so we can go down that. So in the end, if we move that to code, we should be able to simply say, we're going to make these floating point values here, float m12 is one of the ones that change. So float m12 equals, and you can look at the image, we have m0 times tx, and m0 is now matrix get 0 times tx plus, and then we can kind of, and in the end we add matrix get 12. Okay, so it's 0, 4, 8, and 12, which is the top row of the matrix that we're using, and then it's tx, ty, tz, and finally this would be times 1, and tx, ty, tz is simply the final column. So into the final column of the changed matrix, we're going to be putting the first row times the final column, the second row times the final column, the third row times the final column, and then 1 in the end. So copy this. It should be 12, and 13, and 14, 8, 9, 10, 4, 5, 6, 0, 1, 2. So these are the only values that change, these three values. Yes, we need to make different variables here. But now I've just put this into these variables. We can actually see I'm only using matrix get 12 here, and I'm not using it again. So we don't even need these variables. We could actually say matrix dot put in the index 12 we put this number. So into index 13 we put this number, and into index 14 we put this number. Okay, so we can allow ourselves to do this here because we can see that we're not affecting anything that will be used later on in this. If we're going to do a more complicated matrix multiplication,
so what are you doing this one? Oh, okay.
do you want to have time to look at that and do it yourselves, or should we just roll on through? Okay, so now we've added a translation to our matrix. Now let's see if we can actually set up the program to use this model matrix rather than what we're using already. So if we go into our main game class here, let's see if we can comment this out, this model matrix thing here, and say instead we want to, let's just set this up as a single model matrix here. Just stick it in here. Say we have a private model matrix, and we'll call it model matrix. No, like so.
You have two of the same.
I have two of the same. Okay, I have a float buffer called model matrix. So I'm gonna comment this out, and I'm gonna rename this then. Vector rename and call it model matrix buffer. Fine. I'm sure it's, yeah, okay, it's being used here. We're going to want to just get rid of that in the end, but let's leave it there for a while.
So, in that sense, couldn't we just get rid of this essentially become useless once we're done?
Yeah, the model matrix buffer here will essentially become useless. And the stuff we're using there. I'm going to see how this runs right now because we're using that. Okay, it doesn't run right now, obviously. Okay, some of this. Yeah, it's using the buffer here. It's setting the buffer here, so the buffer hasn't been set. Once we get lower, let's leave this in here and just take it out once we're sure that we're using the other stuff for everything. Errors. Oh, great. Model matrix buffer. And model matrix buffer. Sorry about that. Okay, so just to make sure that something's running here. Okay, we have what I was experimenting with yesterday, basically. Okay, so that's nice enough. One thing I added was this class here. No, not this class here, which is called coordinate frame graphic. And what it does, it makes kind of a little image of a 2D coordinate frame. It makes two vectors pointing straight to the right and straight up. And I can show you what that looks like here. Let's create it first. It's called coord frame graphic.create. I'm still using these static classes, but if you feel better using instances, that's fine. Okay, so instead of what we're drawing here, we can actually have that in there as well. Go ahead and do set model matrix. Well, let's just clear the model matrix. Clear model matrix. And then coordinate frame graphic dot draw plot. Okay, like so. I'm only drawing it in the second window, and we'll actually see that if I run it now, we don't really see anything because this is the area that we're displaying in this window, whereas the graphic I'm drawing is down here in the corner. So I'm just going to change the orthographic projection we're looking at here. Just go from, let's say, -5 to 5 on both axes. -5 to 5, like so. Any of that? Okay, you can move this out of the way. And so we have this little coordinate frame here. You can even take this and say, let's make it -3 to 8, or -3 to 7. -3 to 7, just to have a bit more room above it. We can even leave the red box there, and you can see the graphic over there. Okay, so this is what we're going to start with translating or transforming. We're going to have this little coordinate frame, and then we're just going to add transformations to that. Yeah, okay. Before we take a break, let's see if we can get just a simple transformation to work now. So what do we want to do then? In the create function, we want to say we have this model matrix at some point here. Just as well do it at the bottom here. We're going to say model matrix equals new model matrix. we can actually call model matrix dot load identity matrix just to start it off like that. And I'm going to see if this runs without crashing. Yeah, okay. Doesn't do anything. So okay, we load the identity matrix. From now on, we're going to work with this inside our display function. So the display function, which is called from the render function. So now we're not going to use this clear model matrix. Instead, we're going to use our model matrix class and call, let's just load identity matrix each time in the beginning, because we know if a frame has run, whatever happened to it then is still there. Model matrix add translation, and we'll just move it 3 to the side, 2 up, and let's ignore the Z part, but let's do it like this. First draw one with the identity matrix, then we add the translation, and then we draw another one. So hopefully, wait, what? What did I forget? I know it. Who can tell me what I am not doing here that would make OpenGL not know what it's supposed to do?
No XYZ coordinates in the translation?
I'm making the translation correctly, but I'm not really doing anything with it. I'm just putting it into my matrix. I made a matrix class, and I just put in numbers there. So I'm changing floating points around, but I'm not really doing anything with it. What's missing here is model matrix dot set shader matrix, and we have the was it model matrix lock here, and I need to do that every time I have a matrix that I'm satisfied with. I need to send it into the shader, so hopefully this will work. Okay, so moving this out of the way, we have the base one there, and then we have one that's moved 3 to the right and 2 up. Now the interesting thing here, compared to what we were doing earlier, because then we're just setting a translation or setting a scale, and whenever we set a new translation, we'd overwrite the old one. Anytime now we add a new translation, so if I just copy this entire thing and say, now I'm going to translate -1 and 1, and then I'm going to draw it again. So I'm adding that translation. So this one here has no translation. This one here has a transformation that is a translation by 3.2. This one here has a translation that's -1.1
From the second one.
from where it was added. However, if I were to do the same thing here, but instead do model matrix dot load identity matrix before I do it.
Then we reset.
Yeah. Then I reset so that this one here is the base one. Then I add a translation of 3.2. Then I add a translation of -1.1. Then I reset to 0. Then I add a translation of -1.1 and draw this one last. So every time I add a new transformation, it's being added to the transformation matrix. Let's take a short break now, and then we'll look at doing this with rotations and scales, which will be that much more interesting to add up. Make stacks of rotations. Okay. In the break we were talking a bit about shaders, and just for the short version of that, the idea that we're working with right now is that the values that we're putting into our matrix here, or our model matrix, the values that we're putting in there don't really mean anything until we actually tell OpenGL what to do with them. So we have the shader, and we can just look at that here. Just look into the vertex shader here. Why did it open? Oh, never mind. Okay, so this is the vertex shader. It's just a bit of C++ code, more or less, very simple C++ code. And it has this variable here, model matrix. It has a variable projection matrix. Both of them are this matrix 4. It's a specialized version of C++ here. This is vector 4, so it's simply a 4-number vector for color. And these three things are values that we need to set. So when we call set shader matrix, we're calling something that tells OpenGL, here are values that we want you to put into this variable here. And when we call it for the projection matrix, we wanted to put it into here. When we're changing the color as well, we're telling OpenGL, there's a color variable in the shader. We know where it's at. We have this location pointer to it. And we want you to put the values that we're sending into this vector here. So once we've done that, we've set some values to the model matrix, the projection matrix, and the color. Every single vertex that goes through the OpenGL pipeline will first be sent through this vertex shader. This is kind of the first part of the pipeline. Then a lot of stuff happens, and then the fragment shader happens later on. But the fragment shader is a bit more of a complicated idea, because for each vertex, or for each primitive that we send in, the fragment shader can be called multiple times. But the vertex shader is called once for each vertex that we send through. And that vertex will simply, so this attribute here, position, that is the vertices that we're sending in. We send them in as buffers, and each one will go through this code once. So we get a vertex. The first thing that we do to it is that we take, in this case, we simply eliminate the z value, only use the x and y value. This is a very simplified 2D shader. Then we say we take the model matrix, which is exactly the values that we're working with in this exercise here, and we multiply that with the position. So we're simply multiplying the position with this matrix and putting that into the position again, saying this is the actual position now. So the position was whatever vertex we sent in, but we want it also to be multiplied through the model matrix to get the true position here. Then we say we have color. We set that into vColor. And finally we say GL position, which is a fixed variable, which is the variable that tells OpenGL this is the final position that you should work with throughout the rest of the pipeline. We send that through the projection matrix as well. The projection matrix is setting up which window we're looking at our world through. Okay, so that's what the shader does. We'll make more complicated shaders, but for now, this is what it does. The final thing here, the varying, that is a value that's used both in the vertex shader and in the fragment shader. So by making a varying variable and setting a value to that, that will be sent through the rasterization process, and we'll get to edit the values from that again in the fragment shader. Otherwise, this is input. The attribute is input that comes in through buffers. Varying is output from the vertex shader that gets used again in the fragment shader. Yeah, and GL position is just an output variable that OpenGL uses throughout the pipeline. Do you feel this clarifies the shader at all? The main thing is that we're going to be using this variable model matrix here. That variable is set to a specific position here, U model matrix, and we have this pointer model matrix location, and that's what we send into the shader matrix pointer. So that's simply just a value that tells OpenGL we have a handle to this matrix. Here are the values that we want you to put into it. Okay. Cool. So, what we had was the fact that we're actually translating stuff. And we're translating it, and then we can actually clear the transformation matrix, put it back in. Another thing as well, just to make that clear, wait, here. We don't actually need to call set shader matrix after every call to a change in the model matrix. If we want to skip drawing this one, okay, if we have, let's say we just have a couple of transformations we want to do. We want to go, we've gone to 3.2, we're going to go to -1 from there, and then model matrix dot add translation, just go straight up by 2, 0. This doesn't make any sense, obviously, when we're only using translations. We'd always do it in one go. But here we're adding 2 translations, 2 transformations, then we set the shader matrix. Just whenever we have a matrix that we know we're going to use, we'll set it to the shader. It means that we don't have to constantly be talking to OpenGL and constantly be setting values inside our graphics hardware. That's basically what we're doing here. We're working with these matrices a little bit just on the CPU, but when we send them to the shader, we're sending the values down to the GPU for it to be used there in a much quicker way. Okay, so this looks like this. So we have 3 transformations in this one. The first one to here, when we draw this one, then one to here, then one to here. Anyway, let's add some more interesting transformations before we start working with the rest of this. So, model matrix again. So, let's add scale. We call that SX, SY, and SZ. Again, so another interesting way to view the fact that we only had to change places 12, 13, and 14 here is that they're the 4th column. And the 4th column is the point of origin of the coordinate frame that we're working with. And when we add a translation, we know that it shouldn't change the direction of the axis. It shouldn't change the size of the axis. It shouldn't change the vectors at all. We still have the same orientation and the same size of the coordinate frame. The only thing add translation should change is the position of it. That makes sense, and that's the reason why we can only change these 3 things. Also, we kind of showed it mathematically as well. So when we add scale, we should be able to say we're probably not going to want to change 12, 13, and 14, because we're not going to want to change the position of the coordinate frame that we're working in. The scale should only resize it, but it should leave it exactly where it is. And let's see if this ugly OneNote image here can be used again. You could erase the lines that tell me where the recording screen is as well. So again, we have, oh yeah, cool, thanks. Could actually have it a bit higher, never mind, let's leave it here. Okay, so we're going to be adding a scale, which is SX, SY, SZ, and then we just have zeros, 0, 1, in this stuff. Okay, we have M0 here, we have M1, M2, and a bunch of other stuff. So what we're going to get out of this, we can actually just look it over a little bit before we start this. we could, as before, we could just make this entire matrix, and then we could call a matrix multiplication. And that, in some cases, is simpler code for us. We can make it a bit simpler here. You can see that for this value here, we're going to be multiplying this times Sx plus 0 times whatever's here, 0 times whatever's here, 0 times whatever's here. So simply whatever was already here times Sx. Okay, if we go down to this spot, that'll be this times Sx plus 0 times whatever's here, 0 and 0. Okay, so the same is happening here. Just whatever's already there times Sx down this column. So Sx is affecting the entire x-axis of our coordinate frame. That makes sense. If we go to the next spot, we'll see we have this times, oh sorry, this spot would be this times 0 plus this times sy. So we have the y value here. So whatever's here already times sy plus this times 0 and this times 0. And so we're going to end up with that. So we have the y scale affecting the y-axis, the x scale affecting the x-axis, and the z scale affecting the z-axis, and nothing affecting the point of origin. And none of these are affecting each other, so again we can go into our code. We should be able to say matrix put into the index 0. We're going to put the value matrix.get at 0. We can say Sx times whatever was there already. Okay, so for 0, 1, and 2, this is true. Index number 3, index number 3 was the bottom left corner of the matrix, so that's still just 0. So 4, 5, and 6 will be affected by sy. And then we have 6, 7, 8, 9, and 10 will be affected by sz. And so we leave, in the end, the entire, we leave the entire bottom row, and we leave the entire last column. So we're just looking at these 3 numbers, these 3 numbers, and these 3 numbers. So let's hope this works.
Will it be by the second 3 matrix? Yeah. It's 5.
Yes. It's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and then 12, 13, 14, 15. Doesn't that make sense? So 3 is unchanged, 7 is unchanged, 11 is unchanged, and the entire column of 12 to 15 is unchanged. Okay, so let's see where this leaves us. If we can go in here and say, okay, rather than adding these silly 2 translations here, let's just make it -1 and 3. So we've put them together. Model matrix dot add scale. Let's just do it simply first. 2, 2, 2 or 2, 2. See what happens here. Okay. So we have the first one, then we do a translation to this one, then we do a translation, then we do a scale, then we clear and go back to here. Now, okay, this might end up off the screen, so I'm gonna change it a little bit and say this one actually goes -1. Let's just say -2, so it's going kind of back down again. See how that looks. Okay, so fair enough. That's what it looks like now. I'm going to see what happens if I take this scale here and add it before this one instead. What do you believe will happen? Yeah, it'll affect the next one. We draw the next one, then we load identity again, so it won't affect the last one. But it'll affect the size of it, but it'll also affect the position of it. Because this translation here will be translated in the scaled. So let's look at what it looks like. Okay, so the first one goes, then we translate to here and scale. Then we translate again by -1, -2, which previously was -1, -2 when it translated to here. But now it's -1, -2, translating it all the way down here. So any translation, any transformation that happens in a coordinate frame happens within the boundaries of that coordinate frame, and it happens by the size and orientation of that coordinate frame. And this becomes that much more interesting as soon as we add rotation. Correct. So, and I think for now we'll just add.
So you're scaling the coordinate system as well?
Yes. That's the idea that we're doing this in OpenGL. And that's the difference. As soon as I put in the rotation, we can kind of look a bit more at the difference between how it's viewed in classic linear algebra, which is everything is being transformed relative to the base coordinate system, and what we're doing in computer graphics, which is everything is being transformed in relation to the coordinate frame that we're already in. However, the math is the same. So the difference lies only in which order we multiply the matrices. Do we multiply the new matrix to the right, or do we multiply the new matrix to the left? And I can show you how, the same math can be these two different ideas. So add rotation. Okay, since I'm making all of this in 3D, I'm going to call it add rotation Z, which means we're going to rotate around the Z-axis. Once we go into 3 dimensions, we can add 2 more rotation functions that then make sense, and actually 3 more. One that rotates about an arbitrary vector. But for now, let's do it like this, and we need an angle, and it's around the Z-axis, so we don't need anything more than the angle. Okay, this time around I'm actually going to add one variable here. I'm going to say we're going to have this float array, I don't know what you should call it, temp matrix, or let's just call it M2. And here we'll say M2 is a new float 16. What? 16. The reason I'm doing this is simply that I want to be able to reuse this data. I don't want to be constantly making new and new float arrays just to do calculations. There's no other specific reason here. Now I'm going to do M2 0 equals, and well, what are we going to end up with here? Let's just put all the stuff in. Let's make it like it's a identity matrix. M4, no, M2 number 4 equals 0. 12, 8. Okay, let's just start with an identity matrix here. This is 14, 13, 8, 9, 10, 11, 4, 5, 6, 7, 0, 1, 2, 3. Oops, 1, 2, 3. Okay, and this should be 0, 0, 0, and we have 1 here, one here, and one here. Okay, so here we have an identity matrix. To make a Z rotation matrix, where should we change stuff and what should we put in there? Was supposed to be here. We're not going to affect this column because it has to do with the z-axis. We're not going to affect this row here. And we know we're not going to change the position, and we know we're not going to change the bottom line. So it's these four values, 0, 1, 4, and 5 that we're going to change. So we have the cosine, we have the minus sign here, cosine here, and sine here. I'm going to make float c equals math dot cosine. Now the question is, do we want to send that angle in degrees for ease of understanding, or do we want to send it in radians? It's kind of a tradition of using degrees in OpenGL. So I'm going to say, we'll say it's the cosine of angle times 180 divided by math.pi. So I'm just converting, and it's going to complain because can't convert from double to float. Then I need to, I don't know. Yeah, good enough for now. Okay, let's do the same here. Float s equals the sine of that same angle. Convert it to radians. And then we load the matrix. What do I need to do now? Now I've made this matrix here, the M2 matrix. We could also make a simplification like we did in the other cases so that the calculations won't be just as much. But it's a bit more complicated in this case, so I'm going to allow myself to just say this dot add transformation M2. So this should simply take this entire matrix, multiply it with the entire current matrix as through this code, which is fairly complicated, and then we're just going to have to cross our fingers that it works properly. Okay, so the rotation should work now. And let's see. So let's just put that inside instead of the scale. Let's comment out the scale for now. Or, well, or we can actually just put it in here after this translation. Model matrix dot add rotation z. Let's say 45 degrees. Just to see something happen. Huh. Not quite though.
It's going a couple of percent.
45, that's a bit more than 45 degrees though, isn't it?
Oh, it should not be 360.
1 pi is half a circle. Let's see, model matrix here. What am I doing wrong? It's cosine minus sine, sine cosine. That's correct, right? Yeah. The angle times 180 divided by pi should be the correct conversion. The only thing I'm wondering might be wrong here is then the matrix multiplication itself, which would be fairly hard to debug here. 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3, 0, 4, 8, 12, 1, 5, 9, 13, 4, 5, 6, 7, 6, 7, 4, 5, 6, 7, 8, 9, 11, 10, 11, 8, 9, 10, 11, 11, 2, 6, 10, 14. Yeah, it's correct. Okay, I'm gonna see. I did 45 degrees. Was I thinking a different direction there? I'm gonna try one thing. I'm gonna add the Z rotation. I'm gonna add it earlier, so that we see something else actually being translated after the rotation, so we see in which direction that translates. It's flipping the Y as well. No. No, that was not right. Model matrix here. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 15. Okay, add transformation M2. Let's see if we change this from 45 to 30 degrees instead. Let's just see how much it's changing. It seems like it's let's just make this translation just 2 straight out by the x-axis, then we can see which axis is actually the x-axis. Okay, so we're flipping the y-axis. We're rotating it 30 degrees, but then we're flipping both axes. That would happen because cosine of this angle I'm gonna try one other thing. I'm just gonna say matrix dot put M2 just to see what happens. So I'm just gonna put this rotation only inside the matrix. Okay, that's not buffer overflow. Matrix dot rewind. I don't know. Okay. So it's not in the matrix multiplication, it's flipping already in here. Anybody see errors in this? So the x and y.
Are you sure it's supposed to be degrees?
Well, cosine, this function definitely takes in radians. The thing is, we can see that it's actually rotating about the correct angle. It's rotating 30 degrees, but then it's just flipping both axes as well. And I'm wondering what is happening with that. I'm not doing any scale as well. Alright, didn't want to waste too much time on this. So the thing is, if I do this, which is all wrong, now it works correctly. Yeah, but I'm wondering where the flip happens to begin with. But I'm going to check to see that the same thing actually happens. Okay, fine. Now it's adding to the transformation rather than just putting it. Okay, this is weird, but let's leave it at that, because I think if we can now go up here and just say, okay, we have this position thing, let's make one private float angle. We don't even need to do that necessarily. Well, let's do it anyway. Private float angle equals, doesn't matter, 0. And then we're going to say in our update function, whenever whatever happens, we say angle plus equals, okay, this is not a nice way to do this, but per frame 4 degrees. And then let's rotate, instead of rotating by 30 degrees, let's rotate by angle. Then we can see stuff starting to happen. Okay, that's a bit fast. So let's make it a little bit slower. 0.4. Still happening super fast. Wait. Yeah, I'm clearing before. Yeah, it's loading identity matrix here before it. Z angle. How? No. I mean, how many frames could it possibly be drawing? Okay. Wow. That would actually be amazing if it's drawing that many frames. Okay. So this should more or less work. Yeah. Okay, sorry. Sure. Should probably get this orange circle just somewhere else to begin with. For instance, we can start here by saying the orange circle is at the position x pose, yeah. So you can just say in the beginning, let's have this at 200, 200. Okay. So this is spinning now. Fair enough. So we have a few different transformations here, even though that last one just doesn't feel right. M2.
Because we don't convert the angle right to the radian, because it should be angle times pi divided by 180.
Yes, that is correct. Wow. Yeah, I was correcting from radians to... Thank you for that. I was converting from radians to degrees and not from degrees to radians. Sometimes when you've done something a million times before, you just think that it's in your fingers. Anyway, so let's make this right. It still kind of seemed like it was doing the correct. Okay, this is probably going to be ridiculously slow now. Yes. So it was just some kind of random rotation that we were getting earlier. Just something ridiculous. So now let's get this again. Except what I want to do in the update function now is I want to go ahead and say, let's make this the same speed on every computer. So float delta time equals gdx dot graphics dot get delta time. And then instead of doing this motion 3 pixels, let's say we're going to do, so delta time is the time of the frame in seconds, meaning that it's probably 0.01 or something along those lines. So I want to say how much do I want to travel per second. And I imagine I want to travel like something like 300 in this, in the size that the yellow ball is rolling. So let's change all of this like so, and there.
Wouldn't it be better to have full delta time to create the function?
No, delta time is a new time in every single frame.
Because you're just constantly declaring it again and again.
Yeah.
Okay.
Oh yeah, declaring delta time. I don't know. Yes, maybe. Doesn't matter. Something that's declared like this, especially base variables that are declared inside a function, they'll be cleaned up pretty quickly and nicely. It doesn't need the garbage collection for that. Anyway, so the question is, how much out of a circle do we want to move in a second? Like something like half a circle per second. Let's see what this looks like. Okay, so full circle in 2 seconds. Now, what we want to do now, I can move this around. What I want to basically do now in the final 10 minutes, well, are there any questions regarding where we're at now? Maybe, do you feel like you kind of know what's going on with these transformations?
Why are you rotating both of the things?
They're both rotating simply because the rotation is added here, then we draw something, then a translation is added here, and then we draw something more, but we never actually clean it out. So the question is now we have a way to clean the entire matrix by loading an identity matrix. What we would like to have, I think we'd like to add that here, is, what's the collection for stack in Java again? Stack. Okay. Import stack. util. But is it not something I can just new? Do you remember that? Can I go ahead here and say, yeah, okay, yeah, I know what you mean. I have to say it's a stack of float buffer. And then I want to try to do something like matrix stack new stack of float buffer. Okay, and then I should just be able to push and pop. So I'm going to add a function here, public void push matrix. No. So I'm going to say matrix stack dot push matrix. I'm hoping that actually pushes a copy of it, or does it just push a reference to it?
Yeah, can I see again the stack?
We'll find out soon enough.
For some reason I'm getting the error there.
Okay, you can hover over it and then it'll tell you that you can import something. You have to import
No, it's saying
util stack. I'm going to do it this way anyway.
stack is not generic.
Oh. Yeah. Could. Anyway, let's see. So I'm pushing that on top. If it pushes a copy. Okay. Okay, let's see how that works. What I want to also do is do public void pop matrix. So this doesn't need any variables or anything. What we're doing is we're going to say now matrix equals matrix stack dot pop. Okay, so can you see what I'm doing here? when I push a matrix, I simply take a copy of whatever matrix I have, or that's what I want to do. I'm hoping that this will copy it. We'll see in a while. It takes a copy of the stack of the matrix that we have, and it puts it on a stack. Then we can add more transformations all over the place, but we pushed it at a point that we want to get back to without having to go all the way back and doing those transformations again. Yeah. Then when I pop the matrix, I simply say whatever I've done now is thrown away, and I take the last matrix that I pushed on top of the stack. And the idea here, and now I want to go up here and start working a little bit with the other viewport, the first one here. Okay, so I'm going to throw out these set model matrix translation and model matrix scale, or actually we might want to, what's going on? So here, might just want to change them. Okay, and say instead model matrix dot add translation, like so, and model matrix dot add scale. Okay, yeah, the last number has to be 1 when we're adding the scale rather than 0. Okay, like so. So we don't have time to clean all of the old stuff out, but we'll do that eventually. I'm hoping no. So first model matrix dot load identity matrix, and let's do that here as well. See if that works out now. No, it's all gone someplace else. How did it look before? Yeah. I suddenly remembered. Like I told you earlier, we cannot do this without actually sending it to the OpenGL shader. Otherwise, we're just changing random. Otherwise, we're just changing these random. Okay. I don't really care about the blue square. But okay. Let's now, rather than going to X pos, Y position, let's just say we go to 300, 300. Okay, and we're going to draw the first circle there every single time. So there it is. I guess 250 would be nicer to make it, set it up in the center. Okay, 250, 250. Then we're not going to load an identity matrix again. We're going to draw another solid circle. Okay, so what we want to do is we want to translate to here. Then this scale is only supposed to affect this circle, because this is the size of that circle. So before I do that scale, I'm going to do model matrix dot push matrix. I'm hoping this is going to work. Okay, because this scale is only supposed to affect that. However, after I do this scale and draw the circle, I'm going to do model matrix dot pop matrix. So it should leave this translation, but it should have taken away this scaling. Okay, pop matrix, meaning that if I now translate, let's say something like 30 just to the right, straight to the right by 30, and then we'll set up another scale that's smaller, and then we'll draw another solid circle, and we'll draw it in a different color. Let's see what happens now. Not what we expected to happen, is it? Okay, so we did pop matrix, we did another scale, we did the translation as well. Draw a solid circle both times. Okay, so here's the red circle. Set the shader matrix. Yeah, okay. Model matrix dot add translation was what we're gonna do here. So model matrix dot add scale. Matrix dot add scale 10 10 0. Okay. Scale is, yeah. I wonder if it affected it. Okay, it's not. I'm gonna check one thing here. Yeah, I'm gonna skip the push and pop. I'm adding a translation. I'm adding a scale. Setting the shader matrix, and I'm drawing a circle again. Why is the second circle not happening? Ah, okay, the translation is ridiculously huge because the scale is still in there.
So you're scaling the already scaled.
Yeah.
At 10.
That's what's happening there, but I'm going to see if we can at least get. Okay. Okay, I'm scaling the already scaled by 10. But what we wanted was to see if this would work at all.
What about using the M2 matrix? Or would be the platform?
Yeah, when we're pushing and popping.
Yeah, just copy that one.
Yeah, I know. We're going to need to do that. I was hoping we could do it this way. But so what we're going to have to do is go ahead and say so we're basically going to have to say matrix no, and we have it somewhere here on the other side, model matrix. Well, to make this quick, our time is up, isn't it? Didn't get as far as I was hoping. Yeah, M2. So I don't have the M2 matrix here. I'm going to move push and pop into the model matrix class. And we'll say, I think someplace I have, okay. Then we're going to have to say, yeah, M2 number 0 equals matrix get 0, so we're going to have to do that all the way down. Like so. No. 0, yeah, I know. 1, 2, 3, there it is. do this, then we have M2. Then we need to say float buffer temp equals new, no, equals buffer utils dot new float buffer 16 dot put M2, and then we put temp in here. So that should save it. What we have to do here is we have to say float buffer temp equals pop, and then we need to say matrix dot put 0 temp dot get 0. Yes, maybe, but yeah, we're started. Sorry about that. You can leave if you have other stuff to do, but we'll finish this quickly and get something to run here for those who have time. And I'll put it on the internet in the end, just to finish this up. Should have tested this stack stuff better before I started. Sorry about that. Okay, so we're putting it into the matrix, we're getting it out of temp. I'm hoping this might work now. Save everything, let's go to here. We're doing push matrix and pop matrix, and let's see if... Okay, so something is happening there. Now I'm going to make this 20 again, since I'm trusting that the translation is still here, but the scale should be gone because I pushed here and then I popped back off and did the scale in between, meaning that it's not scaled at this point. So when I translate here, I should be translating in the same coordinates as without this scale. Then I scale it to 10. Okay, so then it goes over there. So let's translate it a little bit further out, like 40, and then we can get to the idea that we're going to do.
So now you're not scaling the coordinates, basically.
No. And the main idea here is that, let's imagine we want to set up a solar system or something like that. I'm going to say, okay, this here is the sun, and after I draw that, I basically pop the matrix, but I leave it at where the sun is. So now I want to do a planet. First, I'd have to add a rotation. Where I'm adding, I'm not adding any rotation here, so let's go down to where I'm not using rotations. Okay, so I'd like to add a rotation here. I translate, first I add a rotation for where I'm at in the orbit. Then I translate. So I'm always translating straight out with X, but if I do it this way, it's going to be rolling around there. So okay, let's put it a bit further out, always by X. But okay, I rotate this, because this is where I'm at in this orbit, this planet. Then I add a translation. Then I add the scale for the size of this orbit. All of this, though, is something I'm not interested in for the next planet. The next planet is at a slower orbit. The next planet is further away. And the next planet is also smaller. And it's also a different color. So just some different color. Okay, so now we have two planets.
Wait, how is the rotation center for those planets?
Why is it rotating around this planet? Because I translate to here, and that translation is still there when I start rotating. So I've translated my coordinate frame to there, and the rotation will happen around the center of that.
Right, okay.
Whereas in classical linear algebra, that would say that's not what you're doing. What you're doing is you're rotating first. That is, you're rotating within this coordinate system, and then you're sending that rotated object and translating it to here. But I say no, I'm actually translating first, then I'm rotating within my own coordinate frame. It's going to end up being the same math, doing the same thing. It's just which one of the matrices do I call first versus which one is second. And so we're always thinking every translation or every transformation that is added is always happening within the coordinate frame that you're already in. So if I'm here, the rotation happens around the center that I'm at. If I now translate by x, I'm going to be translating to here. X is here, so translation by x should be here within this mainframe, but I'm already rotated, so x translation is here. Because I'm always multiplying each new transformation matrix on the right side of the main matrix. Okay, so with these planets, I can then keep on adding by saying something like the second one can also have a moon.
Can you add the coordinate system that spins as well, so we can see it?
Yeah, sure.
How about giving the next one a negative angle? Wouldn't that rotate clockwise?
Rotate the other way, yeah. So, okay, you want to see a coordinate frame draw plot. Do you want me to draw it just instead of the circle? Okay, so there you have a little coordinate system going around. So that's actually rotating as well. Maybe we would actually not want that to rotate like that. We would want that to have an independent rotation. So in that case, we'd have to do push. We'd have to do an extra push matrix here. No, wait. Well, the translation we'd have to translate back actually. So we'd have to take this we'd have to rotate back. So we'd say we add the rotation, we translate to where it is, then we'd actually have to rotate back. And let's see what happens now. Okay, now the coordinate frame isn't spinning. Let's make it a bit bigger. Let's make the scale like 30 so we can see this better. So we have the rotation of the orbit, but now we want the rotation of the thing itself. So then we say, well, before we actually draw this, it's spinning around itself at, let's say, angle divided by 3. It's kind of weird. Or let's say minus angle divided by 3, so it's spinning the opposite direction. Yeah, like that. Okay, so then you have that rotation. Then after we've actually popped that away, however, I might want to say, okay, I push here for this entire system here, but after I rotate to its position, I'm going to push again. So when I pop here, I'm not popping the entire thing, I'm just popping back to the planet. So then I can make a moon for that planet by taking the small planet here, and doing where is that on its orbit around that planet, translating not too far. I'm not sure. Okay, so now we have a little orbit orbiting around the other orbit.
I don't quite get it. How are you rotating around the central point?
So we first translate to here, and then we push that matrix and save it. Then we do a rotation for each orbit. Like for this planet here, we rotate to where it is in its orbit, then we translate to it, then we draw it, and then we pop the matrix, so we're back here. Again, with a regular coordinate frame here, centered here. We've drawn this already. We're still centered here, and we have no rotation. So now we rotate for the coordinate frame that's dancing around there, for its position in the orbit, but we still save that matrix. So when we go out there, we negate that rotation. We do another rotation for where it's spinning around itself. Then we draw it. Then we pop so that that orbit doesn't have an effect. Then we spin to where the small moon here is orbiting. And then we translate to how far away that is from its center. Then we draw that. Then we pop again, and we should be here again. If we finally pop one more time, we should be here. Or we can clear. Or if you're unclear on exactly how many push and pops you've done, you can always end up saying, okay, before I'm going to start drawing in the other viewport, let's just go ahead and do a good old model matrix, load identity matrix somewhere. But if you've done the same amount of pushes and pops, you should be exactly where you began before you did the first push. So that's what you have. And then go ahead and experiment with that as much as you want. Sorry we went so much over time, but I think we're at a point where we kind of visualize the idea of setting up these transformations, saving them where we want them, continuing, backing up, like with the car and the tires example. You go to where the car is, you draw that, but you push the matrix there. You go to where the tire is, you draw that, you pop back to the center of the car, you go to where the next tire is, draw that, pop to back to the center of the car. So yeah, you move to where the car is, and you orient the car, and you scale to how big the car is. Then you push. Then you do the tires each at a time, pushing and popping for each tire. Then you're at the center of the car again, and you know, okay, now I need to draw another car. Then you pop. Then you translate to the other car, rotate for the other car's orientation, scale to the other car's size, draw the car, push the matrix, draw each tire, push, draw tire, pop, push, draw tire, pop, push, draw tire, pop, push, draw tire, pop, pop again, and you're back to the center, and then you can start drawing whatever else is in your world.
How are you keeping track of like the angle of each orbit?
Right now, I'm just doing it in these hard-coded numbers, and I just have this one angle here, and that angle I'm just dividing it by 2 sometimes and dividing it by 3 sometimes, so it's some of the orbits are fast and some are slow. Obviously, to do this in an actual program, you'd hold a separate variable for each planet, and that planet would have its orbit distance, its orbit angle, its spinning angle, its moon orbit angle. You know,
And each rotation is relative to the last one.
Each rotation is relative to the last one, yes. Or each rotation kind of adds to the last one.
How though? If you're popping the matrix, how are you keeping it relative to the last one?
It's relative to the last one before you pushed. If you pop, you're back to the last matrix before you pushed. It's basically a stack. So every time you push, you add to the stack. Every time you pop, you take what's on the stack and you overwrite what you're working with now with that. So the popped matrix is whatever you were working with the last time when you pushed, and so you're back to there. It's just a way not to have to go all the way back to the beginning by clearing and then doing your transformations over again.